Welcome everyone to this week's science news. Today we'll talk about the new superconductor claim, bad news for new physics, a quantum radar, how to print origami, space-based solar power for a moon station, a dire prediction for the collapse of an ocean circulation, Europe's first hyperloop test, why NASA shoots lasers at the rainforest, and of course, the telephone will ring. The biggest science news this week has without doubt been that of a Korean group that says they found a superconductor that works at room temperature and atmospheric pressure. In case you didn't have time to make sense of the headlines, don't worry, I have a summary. On July 22nd, a paper with 3 Korean authors appeared on the preprint server archive titled The First Room Temperature Ambient Pressure Superconductor. That might sound obscure, but in plain English it means basically, please give us the Nobel Prize. A superconductor is a material that has zero electric resistance and that repels magnets. We know a lot of superconductors, but the known ones either require very low temperatures or high pressure, or both. This is why there's this white smoke in the video that's evaporating liquid nitrogen, which is required for cooling the superconductor. If we had a material that was superconducting in an everyday environment, that'd dramatically improve the efficiency of the entire electric grid, could make the hyperloop a reality, and would probably even make a bigger particle collider affordable. The new superconductor allegedly works at temperatures below 127 degrees Celsius. They called it LK99, and no, that doesn't stand for lots of kryptonite, it stands for Lee and Kim, and the year in which they first synthesized the material. The 3 authors of this paper also applied for an international patent last year, which was published in March. It later emerged that the 3rd author of the paper, Kwon, uploaded the paper without knowledge of the first 2 authors. That isn't the only weird thing. Something else that's weird with the paper is that it doesn't contain a measurement for the drop of electric resistivity. It just contains a figure for the conductivity at room temperature. Weirder still, just 2 hours later, another similar paper was uploaded to the archive, this one with 3 more authors, and that does contain a measurement of the resistivity as a function of temperature. But the resistivity doesn't just drop to 0 at a critical temperature, it first drops to a non-zero value and then slowly decreases. That's odd. But at least it does go to 0, you say? Well, as Alex Kaplan pointed out, that's kind of hard to say, because the unit on the vertical axis is so huge that even the resistivity of standard metals would be visually indistinguishable from 0. Now, neither of those papers has been peer-reviewed, but it turns out that the paper was published in April in a Korean journal with all 6 authors. I have found that article somewhat difficult to understand. The 3-author paper on the archive seems to signal some kind of tension in the group about who deserves credit for the discovery. They also uploaded a video that shows how the material kind of floats above a magnet. Superconductors do that, but so do other materials. In the video, you can see that the material seems to be repelled from the magnet on one side, but attracted on the other, and that it at some point briefly falls onto the magnet. They say it's because the material has defects, but I lost hope for this discovery when I saw the video. This doesn't look like the Meissner effect to me. Many condensed matter people have argued that it looks like the material is more likely to be diamagnetic than superconducting. Diamagnetic materials are repelled by magnets. Nevertheless, several groups immediately went and tried to synthesize the material to reproduce the claim, with that around Andrew McCaleb even live streaming their experiment on Twitch. I'm recording this video on Sunday, and I don't know what's going to happen in the next couple of days, so I'll have to make a wild guess here. I suspect that the first reproduction attempts will find that the material isn't superconducting, and there'll be some discussion about whether the stuff was synthesized correctly, and then we'll never hear of it again. Though, if this episode encourages more labs to live stream their experiments on Twitch, that might change the world after all. Scientists from the University of Colorado have made the most precise measurement of the electric dipole moment of the electron, and have concluded that a lot of new physics is unlikely to lie within the range of the Large Hadron Collider. The electric dipole moment of the electron is, loosely speaking, a measure for the shape of the charge distribution of the electron. They did their measurements by holding about 20,000 hafnium fluoride ions in an ion trap with electric and magnetic fields. Then they used lasers to bring the ions into a superposition of two spin states. Finally, they measured the energy difference between the two states. That difference depends on the electric dipole moment. They didn't find any evidence for a contribution from the electric dipole, so that allows them to set a bound which is tighter than any previous bounds. This story has widely been reported as having something to do with the supposed mystery of why there's more matter than antimatter in the universe, falsely claiming that the Standard Model predicts the universe should contain matter and antimatter in the same amounts. This claim goes back to a comment on the paper which was also published in Science, which I find hugely worrisome. If you don't have a PhD in physics, you can ignore the next two sentences, but for the rest of you overeducated bunch, time evolution in the Standard Model is Hamiltonian. The present state is a consequence of the initial state, and the time evolution, of course, does not predict the initial state. Okay, back to the paper. That they didn't find any sign of an electric dipole moment allows them to rule out anything that could cause it, and that includes a lot of conjectured new particles up to energies of 40 TeV. That's well beyond what the LHC can test. That tells us two things. First, chances that the LHC will find anything new just went down even further. Second, it's a good example of how high-precision measurements are a cheaper way of looking for new physics than building larger and larger colliders. Hello. Hi, Rishi. Yes, we do have news from Scotland. 1 second. A new study has found that the Loch Ness Monster isn't a giant eel. They're now looking into whether Bigfoot isn't just a misunderstood lumberjack. That's right, they should first make sure that dark matter isn't a giant eel. I totally agree. Well, thanks for calling in. Bye. A group of researchers at CNRS Lyon has developed a quantum radar for microwaves and has shown that it outperforms its non-quantum relatives. This quantum radar is an example of quantum metrology. That's metro as in meter, and it means it's got something to do with measurement, not meteorology. That's clouds and stuff. Quantum metrology means you use quantum effects to make more precise measurements. That might sound somewhat oxymoronic because isn't quantum mechanics all about uncertainty? Yes, but quantum mechanics also has entanglement. That's a non-local correlation between particles that's stronger than any non-quantum correlation. The quantum radar uses entangled particles of light, the photons. The basic idea is fairly simple, though the devil is in the details. You create a pair of entangled photons, keep one in a quantum resonator and send the other one out to probe for the target. If the target is there, some of the photons come back and you compare them to the entangled partner that you kept. The relation between the two can reveal information about the sample faster than normal photons could. In their paper, they demonstrated that this was actually the case. They saw 20% faster radar detection compared to non-quantum radars. This quantum advantage has been demonstrated before in the visible spectrum, but not for microwaves. Microwaves are much more challenging because in this frequency range there's more noise from thermal vibrations. While quantum radar sounds pretty exciting, this device isn't going to be used to scan the skies for UFOs anytime soon. To begin with, because they did their measurements in a dilution refrigerator, and if we had the UFOs in a dilution refrigerator, I'm sure we could think of easier ways to study them than a quantum radar. Researchers at the University of Tokyo have combined 2D printing techniques with chemistry and the art of origami to create a self-folding fabrication method. They used a commercial inkjet UV printer to scratch patterns onto each side of a heat-sensitive plastic sheet. When the sheet is dipped into hot water, it folds itself into an intricate 3D object, like this hat. This clever manufacturing solution for 3D objects works faster than conventional 3D printing and also wastes less plastics. The Tokyo team says the new method is almost 3 times faster than previous methods and has more than 1,000 times higher resolution, which allows them to create all sorts of geometric knickknacks. That's so cool! Can't assemble that IKEA bed? Just add water. The Swiss company Astrostrom has put forward a 269 pages report on the possibility of building a solar power satellite that could one day supply energy to a moon base. They developed the design as part of the European Space Agency's campaign for clean energy that called for new ideas for solar power from space. The company proposed V-shaped solar panels in a helix configuration that kind of resembles a butterfly. Fully extended, the satellite would be about a square kilometer in diameter. They have come up with a well-thought-out way to build its components mainly on the moon and from lunar resources and leave the assembly in space to robots. The power station would be hovering at a Lagrange point between the Earth and the moon. According to their estimates, it should be able to generate about 23 megawatts of power. That's enough to power a large-scale factory. They think their design will also help scale up space-based solar power into an affordable and environmentally friendly solution for our earthly energy needs. That sounds amazing. Let's put that on the to-do list right after nuclear fusion, quantum computing, and immortality. Research out of the University of Copenhagen suggests that a drastic slowdown in the Atlantic Meridional Overturning Circulation, AMOC for short, could be much more imminent than previously believed. The AMOC is part of a big current system that transports warm water north in the Atlantic Ocean. A slowdown or collapse of the AMOC would likely trigger a significant drop in temperatures across Middle and Northern Europe while warming the Southern Hemisphere. Once the AMOC stops, it could take thousands of years for it to resume. The AMOC should not be confused with the Gulf Stream. I explained the difference in an earlier video. Global warming is a problem for the AMOC because this circulation is partly driven by the difference in water temperature between the equator and the poles, and global warming heats up the poles faster, reducing the difference. The other issue is that the return loop of the AMOC relies on heavy salt water sinking to the bottom of the ocean, and melting freshwater ice dilutes the salt content. Scientists used to think that an AMOC collapse was unlikely to happen in the near future. While its currents have slowed slightly over the past century, the AMOC is highly variable. The current IPCC report says the AMOC is unlikely to collapse before the end of the century with medium confidence. The authors of the new paper now did a new data extrapolation and say that the AMOC is likely to collapse around mid-century under the current scenario of future emissions. These predictions are extremely difficult because the AMOC isn't just one current but many. It's a complex and probably partly chaotic system. However, in recent years, observations have indicated that the AMOC is slowing down and might be approaching a tipping point. Now, that there is one study that disagrees with some others doesn't mean this one's right. It does, however, demonstrate one more time that our understanding of the atmosphere-ocean system is insufficient. We don't even know what changes we need to prepare for. In case you've been visiting Greece recently and think it might not be all that bad if temperatures in Europe dropped, it would probably be very difficult for plants and wildlife to adapt. And no, we can't just grow strawberry ice instead. By the way, if you prefer reading or listening to watching videos, you can now also find us on Substack at sciencewtg.substack.com and on Spotify and many other podcast apps under the name Science with Sabine. Europe's first hyperloop test segment is now in operation at the Technical University of Munich. On July 10th, it completed its very first trial, carrying members of the construction team through its 24-meter-long test tube after being certified for passenger use. The term hyperloop was coined by Elon Musk to refer to a magnetically levitating train in a vacuum tunnel that could reach hypersonic speeds. The test system in Munich is far below reaching the speeds Musk envisioned. The passenger pod in the Munich hyperloop could travel at 800 kilometers per hour. That's 4 times faster than a typical passenger train. Theoretically, the test segment isn't long enough to reach such high speeds. It's hard to test that kind of speed and momentum on such short test segments. The team will now use the segment to study how efficient the magnetic levitation is, how well the vacuum works, and why the thing is called a hyperloop. A team of environmental scientists has studied the rainforest with lasers. They used data from NASA's JEDI mission, that is a laser mounted on the ISS. JEDI stands for Global Ecosystem Dynamics Investigation and has been in operation since 2018. This device scans the surface of Earth with lasers and measures what comes back. This makes it possible to measure heights and structures very precisely, for example, that of forests. JEDI should not be confused with JEDI, which is also something with space and lasers. But while JEDI sense disturbances in the Force, JEDI senses disturbances in forests. Being aboard the ISS, JEDI has the advantage of being in low Earth orbit, providing a unique vantage point to study the world's forests from space. From this position, JEDI's laser can shoot into the forest canopy and collect data, enabling researchers to create detailed 3D maps of the forest structure from the top of the canopy down to the ground. In the new study, they found that most tropical forests have a peak in the number of leaves at about 15 meters, rather than at the canopy top. They also found the forest structure to be simpler and more exposed to sunlight than previously thought. This study helps researchers understand how millions of species in the rainforest canopy might adapt to changing temperatures and collects information about the forest's biomass and carbon storage that's essential for understanding Earth's carbon cycle and for fighting climate change. Thanks for listening. We'll be back next week.